Good morning. Welcome to lecture number 16 for this video course series on silicon and wide bandgap power devices. I'm Professor Ananta Agarwal and my colleague Dr. Arash Salmi is here. We are with the Department of Electrical and Computer Engineering at the Ohio State University, and we would like to acknowledge the support of Office of Naval Research in creating this class. So, last time we had talked about the basic Schottky diode function in forward and reverse bias, and then we had talked about how to make the Schottky diode a high voltage device by adding a drift layer. And once we added drift layer, we had talked about two types of designs, the punch through and the non-punch through design. And we had gone through an example of a 600 volt Schottky diode and compared silicon with silicon carbide diodes. Now, today we would like to show you some simulation results for an actual design of a 1.7 kV silicon carbide Schottky barrier diode. This diode, as you see, is a JBS diode, where this is the main diode anode area and this is the JBS grid P plus, 2 micron wide. And we have shown 2.5 micron JBS grid spacing, but we are going to vary this spacing and see the effect. And as you can see, the current will flow from the Schottky regions in the forward direction, and in the reverse direction the P plus grid will help reduce the electric field in the middle of the JBS grid, as well as it will block the voltage vertically. We have also shown guard rings here, and we'll then talk about the guard ring simulations under reverse bias. So, to begin with, if we look at our punch through equations we had described last time, and we use 1700 volt diode and perhaps add 10% to 1700 volts to give us some margin. Then we come up with 14 microns and 5.2E 15 doping of the 14 micron drift layer. So, what we have done is increase the thickness from 14 micron to 16 micron to give us a little margin. We have assumed the critical field of silicon carbide is 2 megavolt per centimeter, and we have assumed the breakdown voltage is 10% higher than the 1700 volts, so it's 1870 volts. So, these are our simulation parameters, and we're going to use these numbers in a two-dimensional simulation software called Silvaco. And you can have access to Silvaco if you are in an industry. If you are in a university, I'm sure you have access to either Silvaco or TCAD. These softwares solve continuity equation and Poisson equation in 2 dimensions. So, it allows us to do 2-dimensional simulations as in this case. So, this is the first simulation result where we are plotting current versus voltage applied between anode and cathode, and this is the forward voltage, and we have assumed titanium as the Schottky diode, and we have applied positive voltage to the anode with respect to cathode, and you can see that the knee voltage is 1 volt. the parameter here that we have varied is the JBS gap, and that JBS gap is shown here. We have changed it from 1.5 micron to 5 micron. So obviously, if we increase the JBS gap, you will see that there is more Schottky diode area to contribute to the current. And by the way, the Z dimension, the width of this structure is 1 micron by default in these simulations. So as we increase the JBS gap, you can see the current is increasing, and the knee voltage is around 1 volt to 0.9 volts as expected. Now, we have now applied reverse voltage to this device, and the reverse voltage is not mentioned here, but it is 1700 volt, and what we are plotting is the electric field along this vertical line in the middle of the JBS gap as a function of JBS spacing. So this red line indicates the electric field in the middle of the JBS gap right here at this point. And you can see as we increase the JBS gap, that electric field goes up. So you can see when we apply 1700 volt, electric field in the middle of the JBS gap at the Schottky silicon carbide interface is increasing, and it increases all the way to 1.8 megavolt per centimeter. We want to minimize this electric field. The other electric field we are plotting is right here at the bottom of the P plus junction, and you can see that field roughly stays constant. So remember, we want to reduce the field here in the middle of the JBS gap, so we can then reduce the amount of barrier lowering and therefore reduce the leakage current, as we had discussed in the last lecture. Now, if we plot the specific on resistance, which is calculating the on resistance from the previous slide for each JBS gap and multiplying it by the cross-sectional area of one cell. The cross-sectional area of one cell is shown here. This dimension times 1 micron, where 9 micron is the pitch for JBS gap of 1.5 micron, 16 micron is the pitch for JBS gap of 5 micron, and and then there is variation in between. So we have taken this cross-sectional area, multiplied the on resistance from the previous slide, and we have calculated the specific on resistance as shown by this equation here, and we have plotted this specific on resistance with the black line here as a function of spacing. And you can see as we increase the spacing, the resistance drops as expected and explained in the previous slide. So what we are trying to do here is to find an optimum JBS gap at which resistance is small and electric field is not too high. So we have plotted the red and black lines in the next chart at 1700 volt again, and again we are trying to find the optimum JBS gap at which electric field is minimized and the on resistance is also minimized. So, what we can do is plot the product of the R on versus the electric field, that means the product of the black and red lines versus spacing, and that we have done here, and you can see that there is a minimum here, and that minimum is around the JBS gap of 2 micron. So, we could choose 2 micron as the optimum JBS gap, which will minimize the product of the electric field and non-resistance. But we want to be a little cautious, because if we choose 2 micron and if our manufacturing bias gives us 1.75 micron or even 1.5 micron, then we have a very high product here. So, we decided to choose the optimum point as 2.5 micron JBS gap, which is fairly good, very close to this minima, but gives us a little bit of buffer. All right. So, by choosing 2.5 micron, we have minimized the electric field and the on resistance. So, if you look at this, 2.5 micron JBS gap, our electric field is about 1.3, 1.35 megavolt per centimeter, which helps us in reducing the amount of barrier lowering. If this field was all the way up to 2 megavolt per centimeter or even 1.8 megavolt per centimeter, then that will lead to a tremendous amount of barrier lowering and hence very high leakage current. So, our optimum gap is 2.5 micron, and if you plot the current density, so to calculate this current density, we have taken the anode voltage of 1.6 volts, and that would be right here, 1.6 volt. At the optimum JBS gap of 2.5 micron, this is our operating point in forward direction, and we have converted the current into current density by dividing it by the area, cross sectional area, and we get a current density of 250 amp per centimeter square of this diode, which is very reasonable. So, from this current density, now we can design a cell size and the full chip for a given current. So, if you want, for example, 25 amp device, then we can use the current density of 250 amps per centimeter square, calculate the area, and then repeat this cell in 2 dimensions in x and y direction, which we will show you later in the next lecture, and create our footprint of the device. All right. So, now the question is how to design the guard rings. So, we have designed the forward bias case, and now we want to design the guard rings. So, we have taken 2 cases. One case is 46 guard rings, spacing of guard rings is constant 0.8 micron, and our guard ring width is 2 micron, right. So, 46 guard rings, total length would be 133 microns. If we sum up the guard ring spacings, that's 36.8 microns. In second case, we have only used 16 guard rings. The first gap is 0.8 micron, and we have increased the gap by 0.2 micron every time. So, we have spacings of 0.8, 1, 1.2, 1.4, 1.6, all the way up to 3.8 at the very right. And remember, the same guard ring structure is repeated on the other side of the anode, actually all around the anode, but we'll see that when we do the layout. We also made the guard ring width to 4 micron because we need a certain amount of distance from here, edge of the anode, all the way up to the end of the guard ring, because this voltage has to be dropped not just in the semiconductor, but also in the package. So, in the package we will have some kind of polymer here called polyimide, and that polyimide has to block the voltage inside the package. So, if we apply 1700 volt reverse bias, that has to be blocked over about 100 microns. So, that is why we increase the guard ring width to 4 micron to give us 100 microns width of the edge termination. All right. So, we have simulated these two cases of guard rings, and you can see we have plotted the leakage current versus the anode voltage. You can see that the red curve is 16 guard rings and blocks about, I would say, little more than 1700 volt, and then it goes into avalanche. And in this region, the leakage current is coming from barrier lowering, impact ionization, and tunneling, etc., that we had discussed last time. In the green case, our guard ring is now wider. Remember, for 46 guard rings, this spacing is 132 microns. So, we have a lot of area that is contributing to the leakage current, and that is why the green curve is higher, but you can see this avalanche is at 1880 volts. So, naturally the 46 guard ring case is a better design because it gives us almost what we had planned for the Schottky diode, 1700 volt plus 10% extra. So, here is the simulation where we are plotting electric field contours at 1600 volts for the 46 guard ring case, and electric field is plotted along this blue line through the diode in the active region. So, this is the active region of the diode, this is the JBS gap, here is the big P plus band, and then the guard rings start right here, and there are 46 guard rings. So, electric field here should be a trapezoid as we expected, and you can see the maximum electric field is about 2 megavolt per centimeter, pretty close to the breakdown field of silicon carbide, which is what we had assumed in the original design. And you can see that the electric field is generally small. You can see electric field is a little higher here and then reduces as we go across the guard rings. And you can see that here we have plotted the total electric field along this guard rings along this red line, cut line, and you can see that electric field peaks in the middle of the guard ring, and as we go to the right, that peak electric field reduces quite a bit. This electric field peaking is due to the fact that the gap is small, and if we integrate the area under this electric field, we should get the total voltage of about 1600 volt, which is what has been used here for the simulation. So, the value of this peak electric field is not very correct in these simulations because electric field is obtained by differentiating the potential, and then depending upon how good your grid and mesh is inside the guard ring during a simulation, that can affect the peak value of the. So we don't pay too much attention to this peak field, but it gives us a good trend. So here we plot the potential contours at 100 volt step. So you can see at 1600 volt the first contour is 1.6 kV, then 1.5 kV, then 1.4 kV, and so on. And the spacing between the potential contour lines gives you the idea of the electric field, because the closer the potential lines are, the higher is the electric field, because electric field is a spatial gradient of the potential. So everything looks nice, and you can see that the guard rings are progressively taking the potential. The first guard ring is 1.6 kV, 1.5 kV, and so on. And if we plot the potential along the red line here, which is for the guard rings, you can see that each guard ring takes up some amount of potential at 1600 volts all the way, and if we continue this, it will go up to 0 volts. So these guard rings are able to take potential and therefore distribute the total 1600 volt potential laterally along the guard rings. And you can see it's a very uniform steps. That means this is a good simulation with equal spacing of guard rings. And then we have a 16 guard ring structure, and 16 guard ring structure in the active region along this blue cut line. You see the same field distribution, 2 megavolt per centimeter, almost trapezoidal structure, but you can see there are some red colors appearing inside the guard ring. So that means we have some much higher electric field here between the guard rings. And remember, for the 16 guard ring case, we were increasing the guard ring spacing from left to right. So you can see even the last guard ring has some electric field, which should not be the case. And if we plot the guard ring potential along this red cut line, you can see the first few guard rings do not take much electric field, but in the middle where the spacing is higher, the electric field rises to 2.63 megavolt per centimeter. So this field is pretty high and probably not a good design, because silicon carbide will break down in this region. We want silicon carbide to break down in the active region where the field is 2 megavolt per centimeter. So we should design it so that the electric field in the guard rings is smaller than 2 megavolt per centimeter. So that can be achieved with 46 guard ring case, except 0.8 micron spacing may be too high. Maybe the first guard ring spacing has to be 0.5 micron. It is always the first guard ring spacing in this case that takes up the highest field. So if we can make the first 3 guard rings to be 0.5 micron gap, we can reduce this peak electric field below 2 megavolt per centimeter. And you can see the potential contours for the 16 guard ring structure. You can see that these potential lines come very close to each other, and that basically shows that the electric field is getting concentrated there. And you can see how the potential divides up along the guard rings. The middle guard rings take a lot of voltage because these voltage steps are higher, and therefore they have higher electric field as we saw. So let us stop here. This is the overall structure of the Schottky diode that we have simulated and designed. We will have a 1700 volt structure with 2 micron wide JBS grid with 2.5 micron spacing, titanium Schottky, aluminum overlayer, SiO2 passivation, silicon nitride to stop humidity from creeping into this device, thick layer of polyimide, which is an organic material to provide the insulation for inside the package, and then these are the N plus channel stops. Basically, N plus channel stops prevent the electric field from moving to the saw lane where the device is cut. Total number of guard rings of 46, fixed spacing of 0.8 micron, and the total distance from here to here is sufficient to block the voltage of 1700 volt from this edge to the edge of the saw lane inside the device. So we'll describe the structure a little more next time. So I would stop right here for today, but we'll pick it up here next time, and then we'll describe how this diode is made and how this device is laid out. So with that, thank you very much, and I'll see you next time.